Annenberg Media.
What do we touch? What do we breathe? What do we interact with every single day? What does a block of wood have in common with a cluster of galaxies? What are we and all familiar and not so familiar objects made of?
Hello, I'm Sally Balunas, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics.
And I'm Robin Moriarty, a curriculum developer and elementary school teacher from Needham, Massachusetts. Welcome to Essential Science for Teachers, Physical Science, a professional development content course.
While we're not shy about sharing engaging classroom activities or demonstrating effective ways of questioning students, the goal of this professional development course is to help you increase your own understanding of physical science, specifically matter.
Sally, matter isn't a trivial subject. Each year in my classroom, I'm responsible for helping children examine their own ideas related to matter. Not to mention that the study of matter is part of all state and national standards at the K-6 level. In this course, you'll learn about the nature of the universe itself. The course is based around 4 broad themes to help you to become a more confident teacher.
Our first 2 sessions together will introduce us to the ideas of properties of matter, classification, and of modeling in science. We will take a look at historic models of matter and closely examine the model that is used today.
Sessions 3 and 4 will introduce us to the chemistry side of matter to help us to explain physical and chemical changes at a microscopic level.
During our next 2 sessions, we will challenge our model and explore the physics behind matter to help explain the phenomena of rising and sinking.
Our last 2 sessions will bring us to the interplay between energy and matter as we investigate forces, extreme heat and extreme cold, to examine their effects upon matter.
Well, we certainly have much to investigate, so let's get started with today's session.
Preschool children spend much of their playtime interacting with objects around them. Along the way, they gain an intuitive familiarity with different examples of matter. But what is matter? This is a fundamental question that philosophers and scientists have grappled with for more than 2,000 years. It's a question young children enjoy thinking about.
About matter? What would matter be?
Joni Grisham's 1st and 2nd graders in Cambridge, Massachusetts are just beginning their study of matter. As we watch Joni's class, you might ask yourself whether their definition of matter makes sense to you.
One of the things scientists wonder about is matter. What is matter?
It's basically stuff that you can see and touch, and basically not matter is stuff that you can't see, and it's like air is not matter.
There's another kind of matter which would be something matters and you would need it. Like air, you have to have air.
You have to have air.
And you can't live without it.
Mm-hmm. So is what we breathe out, is that matter?
No. Only in the winter, because you can see it, but you can't necessarily feel it.
Sasha?
Yes, it is matter in the winter because you can't feel it if you breathe like this. You can't feel it.
I would think that it has to be something solid. Not like solid, but something you can actually hold. You have to be able to hold it, and what you breathe isn't really like that.
Is water matter?
Yes. You can see it even though it's hard to see, because if you're taking a bath, for instance, you can see your body's under the water. You can feel it.
You can see it, you can feel it.
And I think it's matter.
Matthew?
I think it's matter because you can see it, you can feel it. Also, you can hold it if it's ice, you can hold it. And it's solid when it's ice.
I agree with Jonah. You can hold it for at least like 10 seconds, but you can't hold it for very long. Because it always finds a way out between your fingers.
So, would yogurt be matter?
I think yes, actually, because you can hold it easier because it's thicker than water.
It's thicker than water?
And definitely thicker than air.
Sam?
These students are discussing properties of matter using their senses to explore the world around them. What about size? Is it possible that the size of an object has anything to do with whether it's matter or not matter?
Is the school matter? Yes. I can see it. I can feel it. Can I hold it?
I think the school is a matter.
You think the school building is a matter?
Because two things. You could pick it up with a crane, and if you have 1,000 people picking it up, it'll be easy.
Okay.
I wonder if something this big is matter.
Is something that big? What do you think? Does it matter how big it is to be matter?
No. If it's like microscopic, you can't see it, so I think it matters kind of how big it is.
By the time the classroom discussion had ended, Joni's students had created a series of criteria to define matter. If they could see it, hold it, and feel it, then it must be matter. Let's explore children's thinking about what is and is not matter through individual student interviews. As we consider whether or not their ideas are on track, we'll see if we can come up with a useful working definition of matter. We say working definition because we might have to revisit it and change it later when we get new information and new thinking.
We're starting with children's ideas because their fresh view of the world sometimes helps us to refine our own thinking. While these particular children may or may not be typical of the students you'll find in your own classroom, the ideas they present are fairly typical of children in this age group. We call this section the Science Studio. Keep in mind that we are not trying to teach these children, but are listening closely to the students' ideas.
Okay.
We ask children to group objects into two categories, matter or not matter. Do you always have to see, hold, and feel something for it to be matter?
A shadow? No. Because it's not something you can touch, maybe. Like stuff you can play with your shadow, but you can't really touch your shadow.
Well, here's your shadow on the table here. See it over here?
You got your shadow.
Here's mine. I can touch your shadow. Yeah, you can touch my shadow.
Yeah, but you can't really feel it.
You have to be able to feel it.
Yeah.
But you know what this is? Particle of chalk. You know when you like clamp the erasers together and these little tiny, tiny spots of chalk that float around the room? Is that stuff?
Yes.
It is?
Yep.
Why is that stuff?
Like, you know the heat in your classroom when and it's kind of dark and it's still day and you've got the sun and those little sunbeams, that's kind of stuff. So particle of chalk could be stuff too.
But can you feel it?
No, not really, because it's really small.
It's small, but it's still stuff.
I think so.
Okay.
Air, no.
Why are you so sure about air?
Because air, you can't see air, you can't really touch it, but if it's like a pumper for balloons in your if you like pump your air tire, you can kind of feel it, but that's not really stuff.
You can feel it, but it's not. How if I do this? How about if I do that?
Yeah, you can feel it, but I don't think you can really see it.
Tree. Yes, it is matter, because you could pick it up, and it does weigh a lot, and it does take up a lot of room.
Okay.
Echo.
Yeah.
No, it is not, because an echo, you cannot pick up an echo and see how much it weighs, and an echo is does not take a lot of space up.
Okay. But it does take some space?
It doesn't take up any space.
Any space. Okay.
Let's use this graphic organizer to help us build our working definition of matter. By comparing observed properties against a consistent set of guidelines, we can build a definition that can be applied to many objects and substances.
I'm interested to see how Siddharth applies his criteria when we present him with something that has stumped a lot of people, air.
Air, it does take up space, but it doesn't weigh anything. Not pile.
Okay. Air is not
No,
matter.
it isn't.
Okay.
Wait, yeah, it is. Because you kind of can pick up the air. Because air's all around you. So you can pick it up, and it takes up everywhere.
And does it weigh anything?
No.
No?
So it's in the pile that's not matter.
Not matter. Okay.
Siddharth, like many of us, has no experience that air has weight. If it doesn't have weight, according to his definition, it can't be matter.
According to Siddharth, matter has to take up space and have weight. Let's take a look at these. Can we agree that air takes up space?
Let's conduct a little experiment. Do you agree that this glass is full of air?
Yes.
Well, if it has air inside it and air takes up space, what will happen when I put it upside down in this tank of water? Let's find out. Okay, so we all agree that the air takes up the space inside the glass and prevents water from entering. If I take my finger off this little hole in the bottom of the tumbler, what will happen?
The amount of space that something takes up is its volume. It's something that can be measured in many different ways. What about Siddharth's second criterion? Does air have weight? Perhaps we could decide this with another experiment. But before we do that, let's digress a bit and discuss what we mean by weight.
What is weight? Weight is one measure of how much stuff there is in an object. For example, when you pay a lot for some fancy cheese, you need to accurately measure the amount that you're getting. On Earth, cheese has weight, a measurement of the Earth's pull on that particular piece of matter. This pull or force can be read off a spring scale by showing how far that pull stretches a spring. In the case of this digital scale, weight is indicated by how much the object on the scale affects an electronic sensor inside. In either case, if there's no stuff, the Earth can't pull on the object being measured, and each scale will register no weight.
So it's straightforward enough to measure the weight of a piece of cheese. Measuring the weight of air might be a little more of a challenge. We'll need a sensitive scale. And the fact that air is all around us might affect the measurement. But one way it can be done is by pumping more air into a closed bottle and comparing the weight before and after.
Let's return to Siddharth and settle his question about the weight of air.
Okay. How about if I hold this and you pump?
Okay.
Wait, let's move this a little bit, okay? Okay, you want to feel it for a second before you...
Getting tight.
Getting tight, okay. So what are you doing now?
Pumping air into this.
Pumping air, okay.
I think yes, it is matter.
Okay, why are you saying that?
Because yes, it does make the bottle weigh more, and it does take up room. It's taking up everything in the bottle.
Okay, well let's test it out, okay? Okay.
70.7.
There you go. What's happening?
Air's getting out of it. I think it'll be around 55.3, something like that.
So you're saying it'll be less?
Yeah.
Okay, why don't you try it?
68.5.
Okay.
It weighs 2.2. The air in the bottle weighs 2.2 grams.
The air that we let out?
Yeah, the air that was in the bottle.
Okay. Okay. You were saying as you were pumping that you thought while you were pumping that the air is matter.
Yeah.
And why are you saying it?
Because air does weigh. Like if I picked it up in my hands, I couldn't really feel it. But if you did something like this, then it really would be matter.
So Siddharth determined, at least in this experiment, that air does have weight.
Let's keep our working definition for now. Air takes up space and has weight. We can declare that air is matter, according to this definition.
According to our working definition, matter includes the familiar stuff of daily life: books, toys, metals, food, liquids, and even dogs. Each of these has weight and takes up space. Large objects like the giant sequoia tree are matter. Tiny objects like grains of sand are matter. It's possible to extend this to include things that can't be weighed with scale: mountains, icebergs, rivers, clouds.
How about the moon? We know the Apollo astronauts brought back to Earth heavy boxes of moon rocks. But there are other ways to infer that the moon is made of matter. Please check our website for how that was done.
Now that we have a definition of matter, we can't stop there. If you look at all the things that we've called matter, we see many differences. It would be nice to find a way to make meaningful comparison among all these different kinds of matter.
How do we start?
Well, there's a human tendency to classify, and it's not just scientists, but even young children. When we're confronted with new observations, new discoveries, we seek to organize what we found into categories.
We spoke to Dr. Al Martinez, a science historian at the Dibner Institute in Cambridge, Massachusetts.
It's very widespread to talk about science as being mathematical. It's very widespread to talk about science as being experimental. But one of the fundamental aspects of science, before we can reach those levels, is the level of classification. We need to be able to bring together the wealth of experience, whatever is available to us, and systematically classify it. And we find in all the different branches of science that it is a common, shared, early and important development, a stage in the acquisition of certain scientific knowledge, to actually do that systematic classification, to organize, to find what is it that certain things have in common with other things, what is it that distinguishes some things from other things.
Yeah, sort into it.
In order to look closely at the process of classification, we gave our Science Studio interviewees an open-ended task. We asked them to sort a pile of different candies and place them into categories. Would these children's classification schemes match yours?
So what are you thinking now as you're putting those in? What's that group?
Watch and see.
Okay. So what was that first group that you made there?
It's like a group of I don't know what kind of candy.
But you put those, why did you put those all together? I'm just curious.
Because I'm making groups of different kinds of candies.
You said that first group was all the same kind?
These are the same kind too.
Okay.
This is the same kind. Fat M&M. Another fat M&M. Fat. Let's see.
Can you tell me what you're doing now in the middle of it? What you're thinking?
These are, they're round, and these are plump, but I don't think these go. And I was thinking of doing square, but that would be 3 different piles because this, all that.
Okay, well, let's talk about the 3 piles, and then maybe we'll do 2. So can you tell me again what you did here and what the difference is? You sorted these into 3 piles.
These are round. These are, they're supposed to be square, and these are oval shaped.
These 2, is this oval shaped too?
Yep.
Okay. Okay, so if you were going to say, I sorted them by their, what?
Shape.
By their shape in this case.
Can I sort them another way?
Sure. Now, what did you do here?
These are all reddish. This isn't really red, but it's kind of red. These are whites, and these are yellows.
I see. So how did you sort these then? What would you say the sorting is here?
I would say by color.
By color.
Sarah Nia has made 2 practical classification schemes. Both of her schemes place all of the candies she has in front of her in neat groups, with none left over, and both are consistent. You might say that Sarah Nia used broad characteristics to separate candies, what we'll call their properties.
Some properties can be a characteristic that's part of the very kind of matter an object is made of. These don't change when you divide the object into smaller pieces. In the 4th century BC, Aristotle distinguished between these essential properties and what he called accidental properties, such as the size, shape, and state of the material.
Let's take a look at these cubes. They're all solid with the same size and shape, but all are made of different matter. Aristotle would say that their accidental properties were the same, but their essential properties are different.
Now here's another example. This is a piece of aluminum foil. I can cut it into ever smaller pieces until I would need a microscope to see the tiniest bits, but it still remains aluminum.
Some properties of matter don't change regardless of size. Let's see how classifying physical objects can play out in the classroom. In Boxborough, Massachusetts, Cindy Plunkett's first graders are going to look carefully at different objects and place them into groups. What properties are these students using to guide their classifications? Accidental or essential?
I want you to think about all of those properties that we talked about yesterday. What does it mean when I use that word properties? What does that mean?
Properties it could help you use your senses.
Okay, and using your senses, what do you think you might find out about the things in this bag? Will some things be the same, some things be different? Do you think,
Lots of things will be different.
Lots of things will be different. Do you think there might be some things that you might put together in the same way?
Yeah.
Well, that's what I'm going to ask you to do today. I'm going to ask you to sort the objects. I'm going to ask you to think about how they are alike. So you're going to use all of your different senses and think about all those different properties that we talked about to put the objects together.
Children have a natural tendency to want to classify and put things together and organize their information, but sometimes don't know exactly how to go about doing it. Children typically want to tell you how things are alike, but it's a little bit more difficult for them to tell what's different about objects, and then to think that there might be something that, to take a third object and see how it might compare is a little more challenging for them.
These are sort of like the same, right? Yeah. So we should put like these together. Oh, here. This is circle, and this is circle. Yeah. Well, what about those? Those also have some circles.
Okay, well tell me, what are you going to write for this one? What do you notice about that when you look at it?
Shiny.
It's very shiny. Are there any other objects that you think are shiny like this? Yeah, those are both shiny. Do you think maybe you might end up changing the things that you put together? They are all shiny. What was the reason that you thought that colors would be the best way to do it?
Well, I thought because there were more different colors than anything else I could think of, I thought it would be good to put it like this.
And so you told me that you first started by thinking about what they were used for?
Yeah.
And then you sorted by shapes?
Yeah.
And the last thing that you did was sort by color? So how many different properties were you thinking about when you sorted your objects?
3.
3 different ways. Good. I wonder if anyone did this.
When children were organizing, classifying the objects to begin with, typically they do it using a lot of colors, a lot of shapes, and they're very visual. But then they really began to think more about the function of some of these objects and what the materials were that they were made of.
So this is metal. Actually, this is metal. Yeah. And this is plastic. And that's wood. And that's wax. Oh, whatever. And that's metal. And I still don't know. Yeah, furry.
The students use their senses to discover characteristics of the samples under study. This can be the first step in scientific investigation. Then they sought to find characteristics shared by more than one sample. This required some imagination, another key element in scientific investigation. This kind of investigation goes back at least as far as the ancient Greeks. They sought simple yet all-encompassing classification schemes that could be applied to a wide range of observable phenomena. One such scheme dominated Western thinking for centuries.
In the 5th century BC, Empedocles, for example, believed that everything is made of earth, water, air, and fire. 4 fundamental substances. That idea was adopted promptly and developed very systematically and comprehensively by Aristotle. Aristotle, like Empedocles, didn't believe that you could possibly explain, say, something such as that which is cold in terms of that which is hot. Therefore, he saw in these primary elements, earth, water, air, and fire, the fundamental qualities that, through their transmutations, generate all things we observe. He believed each of these elements had a natural place. Natural place of each element served to illustrate not only the natural order of things, but also to explain the changes and the motions that we experience. For example, you put a rock in water, you see that it sinks, it goes downwards. Aristotle thought that the natural place for the solid matter that he called Earth was the center of the universe, and it was its innate tendency to move in that direction. Water's natural place was above the location of Earth, and above that, Aristotle placed air, and further above, fire. One thing about Aristotle's theory of the elements is that it actually accounts for things that we observe in our everyday life. It wasn't just arbitrary. This theory actually served to explain several phenomena rather plausibly. Not only can we explain things such as, well, flame always tends to go upwards, and rocks always tend to go downwards, but we also can explain things such as combustion. You put a log in the fireplace, and you set it on fire, so we see the fire tends to go upwards, but there's also the smoke. Smoke seems not to move upwards as quickly as the fire, yet they both move in that direction. Meanwhile, at the bottom of the log, pieces of it fall down, ashes naturally tending downwards, again in perfect accord with his theory. Now, if you look even more closely to the bottom of the log, sometimes you're able to discern moisture accumulating, actually little droplets of water. And again, we have what seems to be this composite substance, the log, being broken down into the four fundamental elements: earth, water, air, and fire. In different proportions, of course, all inextricably mixed, but still discernible enough so that we can see the four in rather distinct motions and their distinct locations.
Today, we might think that Aristotle's four elements seem naive, but his views held for many centuries until other explanations provided a more useful system for classifying matter. There's no rule that says our system or any system is the final answer. A scientist only cares which one makes the most accurate predictions. Explanations that make predictions that turn out to be false tend to be modified or even discarded.
For example, Aristotle's description of matter would predict that ice, being solid, would sink. But we know that it doesn't.
Likewise, why would water soak into the ground after it rains if its place is to be above the earth? As people observed exceptions to Aristotle's ideas, it became clear that his scheme for classifying objects was found lacking. What scheme might more accurately account for observations of matter?
While there are many ways to classify matter, one of the most useful is to look at its state. For example, solid, liquid, or gas. The term gas, which comes from the Greek word chaos, was first used in a modern scientific sense by the Belgian doctor and chemist Johann Baptista van Helmont in the early 1600s.
The terms solid and liquid stretch back to medieval times, but it wasn't until the late 17th and 18th centuries that scientists started using these words with their modern meanings.
We're all familiar with the idea of solids, liquids, and gases. Exactly what distinguishes them? Can we develop a classification scheme that separates solids, liquids, and gases by looking at what each state has in common in many different substances?
Let's return to our studio interviews. Which properties do children use to determine whether an object is a solid, liquid, or gas?
A solid is something that will hold together. It holds together. And you see, if something is a solid, then it isn't, well, if something is a solid, then it's probably going to be holding together. And I'm not quite sure how to explain it.
Okay. What else have you heard about solids? You heard about, comes to mind when you hear the word solid?
Solid, like thick, not very thin. Well, like a bone is kind of is solid, and it's not easy to break.
Okay.
It's kind of like stout. It's strong and sturdy.
Emily and David describe a solid as something that is holding together or strong and sturdy.
We'll make a checklist of the properties of solids that they mention and revisit this as we go along.
So Joanna, if you had to explain to one of your friends at school, supposing they asked the question, what's the big difference between liquids and solids, what would you say to?
Solids are hard, liquids are like easily broken through like that.
Yeah.
Solids, they're not.
Yeah.
They're hard. Like for wood, you'd have to use a saw, and for this, you'd have to break it. But this, light touch will do.
Yeah. Okay.
Joanna mentioned more characteristics of solids, including heavy and hard, contrasting with easily broken for liquids. Let's take a look at liquids a little more closely.
Wet is a liquid, so it will just, and it doesn't hold a shape.
All right. Say this right here is this. You have to break it, okay? You have to break it into small pieces. Mm-hmm. So you can like have some over here, some over here, some over here, some over here. But with liquid, you don't have to break it. All you have to do is divide with your hand or anything like that. Just divide with your hand. When you put a liquid into different containers, it will keep that shape. But with solids, it won't keep that shape. It will stay the same. As liquids, they can fill the bowl.
Right.
But with solids, they stay the same. They stay where they are.
Okay.
David and the other children have described a number of properties that distinguish liquids from solids. They feel that solids hold together, are strong, sturdy, heavy, hard, and hold their shape. Liquids are easily broken or divided. Liquids also take the shape of their container.
This sounds like a pretty good description. I'm not sure about heavy, though I can see why it applies sometimes. It might be confusing as a determining characteristic.
Liquids can be heavy, like a 5-gallon bottle of spring water, and something quite solid could be light. For example, this block of foam. I suggest we take out heavy as a characteristic.
Okay, so here's our checklist for solids and liquids. Can this be used in any case to determine absolutely whether a given substance is a solid or liquid? Let's visit Salem, Massachusetts, where Chris Bash is the 5th grade science specialist. We'll join her for the second lesson of the Insights curriculum unit, Changes of State.
Today, they're going to be investigating a mystery substance, and they have to look at it and identify whether it's a solid, liquid, or maybe even a gas. This mystery substance consists of liquid starch and glue, and it has some unique properties that I'm hoping that they will be able to identify.
It doesn't drop. I thought it was glue.
I know, me too.
You thought it was glue? Why?
Because it's white.
How come you didn't think it was milk?
Because it didn't move.
Whoa!
It's sticky.
I
don't know. No.
The big idea for this lesson today is that maybe some things that they think are solids or some things that they think are liquids aren't always just pat answers, that they need to just think about what it is that makes up properties of a substance.
It's sticky and really white. It looks like the egg around the yolk, the white.
Interesting. I like that compare. What makes you think that? Why did you say that?
Because it's usually like slimy-ish and it's white. It is very stringy and droopy. It feels and looks like a marshmallow, like when you roast marshmallows and then after they're really hot, they get really sticky if you touch them and really stretchy.
So like, did you see me make this into a ball?
Yeah. Oh, it's sinking. Yeah, so if I had this, it would eventually go down and turn to flat and go all over me.
Look what's happening to this.
It's like a pancake.
Dripping and dripping. Well, wait a minute.
It's like covering and
So wait a minute. Is this a solid or a liquid?
Solid. It's liquid.
I've used something like this substance in my classroom many times. I think my students enjoy working with it because it doesn't fit our normal expectations of a solid or a liquid. They all asked for the recipe so they could make it later at home.
If you pull on it, it snaps like a solid, breaking. If you leave it alone, it takes the shape of its container like a liquid. Let's see how it fits our chart.
Well, the mystery substance will hold together if it's pressed into a ball. It can be strong and sturdy if you hit it. It can be easily divided. And it will hold together, at least for a while. But if left alone, it will take on the shape of its container. Finally, it will snap if pulled apart quickly. Definitely a property associated with a solid.
Well, where does that leave us? Is it a solid or a liquid? Or perhaps we should add to the states of matter a new form called mystery matter.
I don't think so. There are so many substances that don't fit cleanly into solids or liquids, like butter or tree sap, each one different from the other. Even glass has properties of both a solid and a liquid. We would have to add a new state of matter for each one.
Then we wouldn't have a classification scheme at all. Scientists sometimes call this butterfly collecting. That's when you keep adding more and more specimens to your collection without looking for any underlying order.
Well, one way out is that we could say that some substances don't belong with either the solids or the liquids. They have some properties of both.
Well, this mystery substance, which some people call oobleck, is actually classified as a liquid. This is because if left alone, it will take on the shape of its container. Let's return to the science studio. There is another state of matter whose properties we haven't discussed yet, gases. How might they differ from the other two?
What am I putting inside this balloon?
You just put a gas inside that balloon.
How do you know?
You know how it just blew up like that?
Uh-huh.
Well, there's gas in here.
There's gas in there. Can you tell me about what makes a gas?
Well,
Can it change its shape?
well, you can't move a gas. It's always going to replace itself.
Okay, what do you mean by that? It's always going to replace itself.
Well, the gas is going to, so example, if my hand was here and I tried to move the gas from right here, the gas, I just moved my hand through the gas, and as soon as it had moved, the air from here went and replaced itself, and the air from there leaked in, and the air evened itself out again.
Is that the same or different for solids and liquids? If I move my hand through, can I move my hand through a solid?
Well, you can move your hand through, well, you cannot move your hand through any solids.
Okay, why not?
Well, a lot of solids are hard, are the kind like this paper.
Right.
And you can't just, and I can't just let my hand go whoop through it.
Right.
See?
Uh-huh.
Because it would just break the paper.
Aha, it would break the paper. But this doesn't break the gas.
Right, because the gas isn't whole.
One of the properties of gas that Emily describes is that it replaces itself. Air will move in to fill any empty space. In scientific terms, would this mean that it takes the shape of its container?
I think so. So let's add air to our chart, and by implication, all gases. What other properties might distinguish a gas from a solid or a liquid?
Have you seen this?
I've seen that before.
What is it?
Well, I'm not, well.
Okay. It's called a syringe, and it pushes things. Okay.
I see.
Now, can you put your finger right over the end? Not completely covering it. Do you feel something?
Air, the gas, the air is coming out of there.
Okay, so I'm pushing this. I'm pushing air out of here, huh?
Right.
Okay. And where's the air going?
Well, it had been in there, but you pushed it out and it came out.
Okay, excellent. Now what happens if I don't let the air out? Okay, let's say, yeah, cover it with your thumb. There you go. Keep holding, keep holding, keep holding. Do you see that I'm pushing this? Keep holding, keep holding.
Yes.
Okay, so what's happening to the air there?
It's getting tight.
It's getting tight. Now what do you mean by the air is getting tight?
Now, see how that came out without you pulling it?
Yes.
The air got so tight that it loosened, that it got so tight that it pushed that out. That it pushed that way until it would be loose again.
What if your thumb's over it? So I saw you. Okay, take your thumb off. There you go. Now cover it. And now push. Okay, what's happening to the air in there?
The air wants to push back.
Okay, it wants to push back. All right. Did the air in there change at all? Does it take up more space, less space?
And it wants more space.
It wants more space, huh? How do you know it wants more space?
Because when I'm pushing it to have less space, it's coming back and it wants more space.
Uh-huh. Interesting. Can you do this with water or solids? If I had liquid in here, could I push on that so then it would come back out?
No.
Why not?
You see, the liquid will leak through this crack, through heat. Will find a way to leak through. It's just gonna get so much pressure that it's gonna either leak through my thumb or it's gonna do something to get out.
So, but gas can get tighter, you said in here, right? Can liquid get tighter?
Yes, it can get tighter, and then until it gets so tight that it just leaks. It will just leak out if you get it too tight.
Emily observed that air can be compressed. In other words, a given amount of air can change its volume. If I try to compress the water in this syringe, the only thing that happens is I hurt my hand.
Solids and liquids can be compressed, but to a much smaller extent than gases.
Water doesn't stretch to fill its container like air does.
Okay, let's add this to our chart. Are there any other differences between gases and liquids?
If you wave your hand through the air, it doesn't put up the same resistance as water. And if you blow bubbles in a liquid, they rise to the top because they're lighter.
A given volume of air is always going to weigh less than the same volume of water. We could say air is less dense than water. In fact, it's less dense than any liquid I can think of. So let's put that on our chart and review.
Take a look at solids. There are a number of similar properties listed. Holds together, strong and sturdy, holds shape. Since these are so similar, let's group them together as holds shape. The property of taking the shape of its container is shared by both gases and liquids.
But only gases expand to fill all of the space in the container enclosing them, and gases are much less dense than the others.
Well, it looks like we found a simple set of criteria to classify most matter into 3 categories: solids, liquids, and gases. But are these the only states that matter can be in?
Let's think about conducting another experiment. If we take this block of ice and heat it, what will happen?
It's going to change from a solid to a liquid, water.
Quite right. And if we keep heating it further, it will again change state, this time from a liquid to a gas, steam. But what would happen if we kept heating the steam?
We took a trip to the Massachusetts Institute of Technology to find out.
If I begin with a solid and add heat to it, it transforms into a liquid. If I continue adding heat to the liquid, I'll get a gas or a vapor. And if I continue adding heat to the gas, I'll end up with a fourth state of matter that we call plasma. And plasma has fundamentally very different properties than gas. For example, magnetic fields can push plasmas around. They can apply forces to plasmas. Also, electric fields will drive currents through plasmas. You're probably familiar with examples of plasma already. Fluorescent lights are plasma. Neon advertising signs are plasma. Lightning bolts are plasma. It's an example of plasma conducting electricity from the clouds down to the ground. Most of the visible matter in the universe is plasma, and the sun and stars are examples of high-temperature plasmas. The sun, of course, is very massive, and the gravitational forces on the sun mean that the center of the sun is really crushed and heated to very high temperatures and exists at very high pressures. And under those conditions, you can heat up the hydrogen particles in the center of the sun to enough to produce nuclear fusion reactions. And those reactions release a huge amount of energy. The temperatures we're talking about are tens of millions of degrees, 50 million degrees, 100 million degrees, and any solid container exposed to those temperatures will just vaporize. Well, of course, on Earth, we're a lot tinier than the sun. We don't have the gravitational force of the sun to crush all this matter to huge pressures and huge temperatures and to confine it. So we have to find some other way of confining a smaller amount of matter, heating it up to similar temperatures as the center of the sun, or even hotter, but still be able to confine it some way other than with gravity.
Entering pulse.
Okay, plasma. Lasted pretty late.
Here at the MIT Plasma Science and Fusion Center, we have a toroidal or donut-shaped chamber. Inside, we have a plasma. As you heat our plasma, it produces nuclear fusion reactions. As you heat the plasma more and more, the fusion reaction rate goes up higher and higher, and you get more fusion power out. Eventually, you get more fusion power out in these neutrons than you use to heat the plasma up in the first place. So you're producing net output energy. This energy can then be used to make steam, and from then on it's as any other conventional power production, the steam is used to drive turbines, which then drive generators. How could you possibly confine a very high temperature plasma in the laboratory on Earth? And one answer is with magnetic fields. If we apply magnetic fields to a plasma, we see that it can push the plasma, and we could even imagine using magnetic fields to squeeze a plasma and confine high pressures and high temperature plasmas. And that's exactly what we're doing in the Alcator project. We have a donut-shaped magnetic field configuration, and we use it to confine plasma and then heat the plasma up to very high temperatures to the conditions we need for fusion to take place.
So this is 1.25. Yes.
Someday, hundreds of years from now or so, we're going to run out of fossil fuels. Nuclear fusion, in many ways, might be considered the ultimate source of energy. If it works, it'd be an example of mankind internationally doing something really great for man and for the Earth.
Plasma is the most common of all visible states of matter. Although rare on the surface of the Earth, it makes up 99% of the visible universe. I study a body in outer space that's so hot it's essentially entirely plasma, the sun. Not only the sun, but all stars are made of plasma.
Let's review what we've covered in today's session.
Matter can be defined as something that takes up space and has weight. Since the number of things on our universe that take up space and have weight is huge, It's only natural to classify them. One way to classify matter is by its state. Solids can be defined as matter that holds its shape. Liquids can be defined as matter that takes the shape of its container. And gases can be defined as matter that takes the shape of its container, can change volume, and is not very dense. Plasma is sometimes called the fourth state of matter. Plasmas are far more common than all other states of matter combined. They share all of the properties of gases, but also possess additional properties that distinguish them from gases. We will explore these in a later session.
The content that we've covered in today's session may seem simple enough, but it's a necessary introduction to the rest of our course. The properties associated with states of matter are in addition to the properties that we've already determined are common to all matter, that it has weight and takes up space.
That's great, but this leaves us with a question begging to be asked: why? Why does matter fall into such neat categories? Or rather, what explanation might account for the differences between the states of matter?
Well, that's the topic for our next session of Essential Science for Teachers, Physical Science.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.